Thank you everyone for coming to the session. We're not too busy, so I guess I'll keep it quite interactive. If you have questions, maybe during the session, do not hesitate to already stop me if you feel like. So first of all, I want to say a few words about Plantik. So Plantik, we are a ag biotech company developing advanced plant engineering technologies, especially based on CRISPR genome editing technologies, which I will show a little bit later, the different steps. We were founded in 2019 in France, just before COVID. Today we run R&D activities in France and also in Ireland, which you also see a little bit later, especially for the cannabis part. And our whole goal is to build technologies and tools for what we call plant engineers to together accelerate the development for more sustainable, resilient, and versatile plants. Welcome to the people who just joined us. So the whole point here is that we are more of a technology company, and the technology we're developing can be used for different plants. And we chose to start with cannabis sativa, especially because, well, it corresponds to the criteria that we think future plants should have, which is to be a very resilient plant because the climate is changing a lot, as we all know, and it's sustainable in terms of how it's grown. And also it's a super versatile plant. It can be used for a lot of different things. People here are experts on that. And another important reason is because the cannabis genetic is very behind compared to other big major crops. It is about 80 years more behind because of the prohibition. There's a lot of gap in knowledge and R&D activities for it, which means the new technologies and innovation can add more value to this type of plant a lot more significantly compared to a big crop. So when we talk about building tools to be able to engineer future cannabis, to bring better cannabis varieties, we as a company, we took two ways to do that. The first one is a more classic one, I would say. So we started a cannabis EMS population, so it's like a trait library, you can say. So we took one variety and we mutate the plant, which is a classic way to create, different kind of mutations in the population. We did that in collaboration with University College Dublin, with researchers that really work on cannabis sativa. So from there, we took a variety that is originally the wild type variety, is an indoor cultivar with high CBD and low THC. It's from Switzerland, and we mutated and we generated this population. So one goal there is really to do the data collection so that we can understand the genomic causation between a certain mutation in the genome of the cannabis plant and the traits that we are observing at the end. And this knowledge is really, really important. And I would say this is different from maybe more commercial kind of trait library where we are just focusing on singleizing, like taking out specific traits. We are also trying to generate knowledge and to feed back our platform, which you will see a bit later, to have this analysis and prediction capabilities in future for finding cannabis traits. And after a few years now running this project with UCD, now we already have a few stable traits that could be interesting for introgression. So for people who have breeding programs or have plants that can try to use those traits to be introduced into their own germplasms, their own plants. As an example, so I would like to show. So first one is early flowering. So this is already a stable trait that we have in our library. So as you can see, the plants on the right side. So we have a wild type plant. So this is the original plant, and this is one mutated plant here. So this plant, so in terms of days to flower, it took the plant 25 days to flower, while the original wild type plant took 47 days, which means we are 22 days before. It's about 1.8 times faster than the wild type plant. And what does that mean? Obviously, if we have early flowering, and we're not promising that you see the same thing when you introgress to a different cultivar, of course, but you should observe this type of traits in a different cultivar as well. And what it means, obviously, is if you have early flowering, you might have more rotation in a year to grow the plant. And another thing that we observe is that the plant has much more branches developed, so it's a more bushier plant, as we say, and a bigger stem, about 1 times thicker than the wild type plant. So which also means that we might expect, in general, a higher yield, whether it's in one cycle or if you're in an indoor facility or greenhouse, more cycles in a year to come. And then we have also, so this is basically, we took the plant and we selfed it, as we say. So this is a stable trait already within this variety from the start itself. We also tried to cross it with Finola, so more of a CBD, Finola, more of a hemp variety, to see what it becomes. And today what we also observe is the same early flowering trait. So we have multiple mutants from the library that are showing this early flowering trait from 7 to 20 days, between 7 to 20 days earlier compared to the wild type plant. At the same time, we also observe the same kind of bigger stems and more branches and taller plants kind of traits, which means potentially we're looking at a kind of optimized outdoor CBD hemp kind of variety. It can have the good CBD ratios because we started with a plant like that, and it takes in the hemp kind of traits to have a better fiber production, for example. And early flowering is also super interesting because we've heard from a lot of hemp growers, especially in the north kind of regions, that at the moment there's only one cycle, one production in a year, of course. And if we can bring early flowering traits, perhaps we can have more than one cycle, have more of a rotation crop as well. That's what we also heard from the field as a hemp crop. So yeah, that's also super interesting trait that we find. And these traits, basically, we can expect them to be stabilized as of end of this August. So if there's any introgression trials to be held, as from that point on, we can already do it. So this is kind of the first part when we start to mutate the plants, try to generate knowledge, generate a lot of data, try to understand what is happening with the plant in its genome, which is a knowledge that is quite lacking for the cannabis sativa plant. And the second part, I would say, is a more fundamental approach. We are, as a company, we're really building this genetic engineering toolbox, not just for cannabis, but we started with cannabis and everything is modeled after cannabis. The goal is really that we can have this tool set to be able to single out a trait that interests us, whether it's for chemical production or agronomical traits or for resistance to biotic or abiotic stress. We can be able to do that with much more ease. And this more fundamental approach, so how we do that, essentially there are three major steps. The first one is to build a platform that is for the genomic discovery or comparison and prediction soon, for understanding what are the best kind of targets in the genome of the plant that are responsible for the traits that we were looking for. This is a fundamental work, and today we understood even for bigger crops such as tomato, which is also a crop that we work with, this is actually one single bottleneck that the industry has at the moment to understand what are the best targets to use the genome editing on. So the editing itself is something. It's a technique, a protocol. It's difficult sometimes, but understanding where to start is actually the hard part. So what we have done, especially with the library that you have seen before, is to understand this causal link between specific traits, how like CBDs, THC are produced from which kind of pathways, but also for architectural traits for resistance to different pathogens, for example. So here we build a platform so we can help others to find the best targets, the best strategies to perform genetic engineering on the plant. And the second part of coming from there, when we have a good sense of the target, we have to do the guide design. So what does that mean is that we have to design this machinery of CRISPR genome editing. And this machinery should work to go into the plant tissue to make the edit happen. And here we have developed our own tools that we can now do fast cloning for any plants. It's kind of a plasmid bank that we produced. We can clone cannabis very quickly, but we also work with other plants, and it can also happen fairly quickly. And from here, we need to go to the last step and the other kind of critical part, which is the transformation and the regeneration of the entire plant from the edited cell. You will see a little bit later like how that looks. And this part is crucial because today, what is really hard in this part is that most of the cannabis plants edited, they will not survive the process, they will not regenerate, they will not grow from the edited cell, which you will see in the pictures later. So from this whole process, we can expect around 12 to 24 months, depending on the complexity of the trait, one trait or several traits, to have this tool set to be able to target specific things in the cannabis plant and to kind of go for the results, whether it's a single, no problem, coming from here. Whether it's a single target or multiple targets editing. So what does that exactly mean in a process? Just to show you a little bit. So the first part that we need to do is we need to take seeds, we germinate them, and then we prepare the explants. So this can usually happen with different tissues, but we will take the tissues around the first leaves, so true leaves, hypocotyls, or cotyledon. So here, after the preparation, we will start the step called transformation. So the transformation, basically, we have the CRISPR machinery that we designed using what we know as the scissor, but it's just, kind of the machinery itself with the guide design and with the CRISPR itself. And the classic way, so today what we know most of from publication is doing a very classic transformation that is mediated with this medium called Agrobacterium. And what does that mean is, you put the CRISPR machinery and with this medium, and you put all this in a petri dish with the different explants, so the tissues that you choose, and the CRISPR starts to do its editing on the tissue of the plant. So from here, we do the cultivation. So it's in the petri dishes, as you see. And this step is the transformation step. So meaning that the cells are being transformed with what we put as an editing medium. And then we come to the really difficult step, the regeneration step. Today is the bottleneck. So from here, we need to induce what is called a callus. So this tissue here, they need to become the callus. And if there's no callus, they cannot grow the shoots from it. So this step is really, really difficult today, as you can see from the different, so from publication, what is the success rate? So callus induction is only 6.3%. And then from the callus, you have only 1.8% of shoot induction, which is really, really low. And this is because we know that cannabis is a callus-resistant plant. So some other plants, they live through this process really, really well, but cannabis is known to be really difficult to be induced into this callus form. But if we're successful and we have shoots, the plants then they can root, which means we have an edited plant that grew, and it should show the traits that we are expecting to see. So this is kind of the classic process to do it. And you have understood that the bottleneck today, what is really difficult, especially to induce the callus here, and the rate is really, really low. So as a company, I mean, other companies might also work on that. We just wanted to share like what we have achieved so far. So we have developed a different protocol from this classic protocol, especially in the selection phase. We do not use antibiotics. It's an antibiotic-free process. It's a bit technical, and I'm not allowed to share every detail about it. But what is important is to see that actually with the conventional protocol, we repeated it. So what you see is that, so we have, when we repeat what is in literature, we have around 10% callus induction, which is a bit higher than what is published, but it's in the same line. So 6.3% to 10%, around the same. But with our own protocol, what we have seen is already we have a way to visually already tell if there's a transformation. So in the classic protocol, you cannot tell until you have this callus. So if you have the callus, you know that, okay, the transformation is successful, and now I have a callus. So it's kind of mixed together. But with our protocol already, we have a way to tell if the transformation happened. The success rate is today around 28.9, so 29%. And in terms of callus induction, we have 98% of callus induction. And we really think this is because we do not use antibiotic in the process. And all in all, we would have transformed callus at around 28.4%, well, which is the multiplication of those two numbers. So, which is, yeah, around almost 3 times more kind of successful than the conventional protocol that is published today. And the meaning here is that if we want to target specific things in cannabis using this protocol, we will have a much better success rate, less kind of resource to do it, and we have a visual way to tell which are the cells that are actually successfully transformed. So to be able to tell that, it saves a lot of time and money and just effort. So we are now today waiting for the kind of shooting period, which should happen in about a month if we follow literature. But we are quite hopeful, and we think that we have something at hand that is a really good tool to work with cannabis traits, cannabis genome, and try to single out different traits. So this is, yeah, where we are, especially at today. So to kind of summarize a little bit, we have taken 2 different routes to approach the genetic engineering of cannabis. One is the more classic way. People use it on other crops, which is to create an EMMS library with different mutated plants and try to see what traits could be commercially valuable today, but also to understand the causation between genetic elements and the traits. And here we have a few traits that are interesting today. If any of the breeders or companies that use their own plants are interested to try them out or introgress into their own plants, we're open to discussion. So we have early flowering ones for indoor and outdoor plants. We have traits related to bigger stem, more branches, which means higher yield, and a type of CBD hemp with higher CBD and also more fiber production, which we think is a really interesting type of plant to grow in Europe. So this is kind of the case where it's the EMS library and more classic. And on the more fundamental tool building part, we have built this CRISPR genome editing tool for cannabis. Today, we can already use it to accelerate classic breeding. So it doesn't mean that we need to do the entire workflow, because as you might know, in Europe today, we still haven't changed the regulation. So if we touch the genome of the plants immediately, then it becomes, unfortunately, GMO today in Europe. It's not the case elsewhere. For example, in US, no, but also more close to us, it's changing in Switzerland and the UK. But we can use the workflow already to understand the plants better, to try to accelerate the classic breeding using the insights coming from the workflow. So, which means we validate certain assumptions we have, we validate the causation, and we use the knowledge in a more classic breeding setup. And if we use the entire workflow, of course, we can engineer specific traits. So we have a lot of kind of interest in the pathways that lead to different chemical production in the plant. But we also use it to work on more agronomic traits, more resistant to pathogens. It's coming, it's already here for cannabis, but any plant that will be grown in a more kind of compact setup will have pathogens. And the success rate, as I showed before, seems to be much higher, and the tools are more effective. So we can really use it to engineer different traits in the future. So this is, what I had in mind to show today. Quite complex, maybe a little bit technical. I don't know if any of you have questions on anything that I showed. I'll be happy to take some questions. Thank you.